Second kind of collision we'll be concerned with in Chapter 6 is the perfectly elastic collision. Although most people would just say elastic collision, I like putting the word perfectly in there. It just kind of makes a good match, but contrast to the perfectly inelastic collision. Let's see what we have going on in this problem. Here we have an initial and a final setup. Object 1 initially is moving to the right. Object 2 is moving to the left. Had to draw something, again, it could be that they're both moving to the right and it's a rear end collision or something like that. And the objects collide, bounce off of each other. I usually, because at this point I have no idea what direction the masses are moving or different directions or exactly what, I usually just pretend that the masses are moving off to the right and then I let the math figure it out for me in the end. Half of this problem is conservation of momentum. Momentum is mass times velocity. Total initial momentum is going to equal the total final momentum, so mass times velocity, and so on, filling in the equation. But the second half of this is conservation of kinetic energy, modified. Conservation of kinetic energy, well, with the objects moving in the horizontal, all of the energy of interest to us, at least, is kinetic. And in the perfectly elastic collision, what that says is that whatever kinetic energy was there to begin with, it's going to be there at the end. None of the energy tried to sneak away, being converted into heat or distorting the objects, crunching whatever the objects are. For instance, some of the energy would go into that deforming process. Anyway, conservation of kinetic energy modified would make use of 1/2 mv squared, the kinetic energy, but it turns out in the one-dimensional problem, perfectly elastic collision, that conservation of kinetic energy equation can be combined with the conservation of momentum equation, and you can grind through a good bit of algebra and you get a new equation out. I like to call it Koch modified. I like to remember that it's coming from the conservation of kinetic energy, but in appearance, it's very different from that. It doesn't look like energy at all. In fact, a different name for it would be that this is a relative velocities equation. And we have the velocity of object 1 initial minus the velocity of object 2 initial. It's going to equal the same thing in the final, except it's the negative of it. Since these are component equations, it is significant to us what the positive direction is. Make sure that the velocities we put in have the correct signs. Let's switch over to concrete values. Here we have 9 kilogram mass moving to the right 12 meters per second in the initial setup. 15 kilogram mass moving to the left at 8 meters per second. And in the final, well, there's still 9 kilograms and 15 kilograms. Don't know the final speeds. Don't really need a subscript, the F subscript at this point. So I'm just calling this speed V1 and this speed V2. We can go back down to the conservation momentum and the Koch modified equations and plug in. Here we have 9 kilograms times 12 meters per second plus the 15 kilograms times negative 8 meters per second. That velocity is to the left in the negative direction, so we need to substitute in negative 8. It's going to equal 9 times the final velocity of object 1. Remember, we dropped the little F subscript. Plus the 15 kilograms times the final velocity of object 2. In Koch modified, we have the V1 initial minus the V2 initial. That's going to be 12 minus negative 8. Will equal the same thing. Don't have any concrete numbers to plug in here. Here we have 2 equations, 2 unknowns, and we need to go through that solution. I'm going to grab those equations, say goodbye to the pictures, I guess. Let's focus on the math. Grab those equations. I've rewritten them here. And probably the best first thing to do is just simplify them a little bit. In the conservation of momentum, we can simplify the left-hand side. So we have negative 12 equals the 9v1x plus the 15v2x. If we're doing this by hand, we can make life a little bit simpler by realizing that we can divide every term by 3, and then also flipped it around to put it in standard form for better or for worse. With the Koch modified, 12 minus negative 8 gives 20. We can distribute the negative across the parentheses, and that gives negative v1x plus v2x. And to put it in standard form, I just flipped it around. So we have the variables on the left and the 20 on the right. In solving this, we want to take one of the equations, solve for one of the variables. Well, the second equation is simpler than the first. It'd be very easy to solve for one of the variables. In fact, let's solve for the v2. Take the negative v1 to the other side, so the v2 becomes v1 plus 20. And then we're going to substitute that value into the other equation. Our other equation, I've grabbed it here, 3v1 plus 5v2 equals negative 4. Anywhere I see a v2, v2x, I'm just not, for the most part, saying the subscript as I talk through this. Anywhere I see the v2x, I can replace it with v1x plus 20. So we have the 3v1 plus 5 times the total quantity, v1 plus 20 equals negative 4. That gives an equation involving just the one variable, v1x. We can distribute the 5 across the parentheses. So now we have 3v1 plus 5v1 plus 100 equals negative 4. Combine the 3v1 and the 5v1 to get 8v1 equals, at the same time, I subtracted 100 from each side. So on the right-hand side, negative 4 minus 100 gives negative 104. Divide both sides by 8. Just by coincidence, this works out nicely. So the final velocity of object 1 is negative 13 meters per second. So object 1 is actually moving to the left. Once we have that equation, we can go back to any earlier equation that involves both variables and solve. The easiest one of the earlier equations would be the v2 equals v1 plus 20. But I now know the v1 is negative 13, so substitute in, and the v2 is going to be 7 meters per second. So object 1 bounced off, moved to the left at 13 meters per second, or the velocity is negative 13. Object 2 bounced off, it moved away to the right with a final velocity of positive 7 meters per second.